Great. So, sorry. So we finished, or we didn't quite finish. Last time we finished today, trying to understand what's going on with this phenomena we're seeing here. And to remind you, part of kind of what we want to get to is how much of this is kind of fits with our classic understanding of statistical learning, and what we need to, what questions do we need to answer to put it within our standard understanding, and what maybe goes beyond our standard understanding. And we said the first thing we noticed is that we're succeeding generalizing using these huge models that can fit anything that can be falsified, can fit even random labels. And we said that's fine. I mean, this is the same type of behavior they get even with something like a hard margin SVM or a minimum norm predictor. And because really what's going on here is, in some sense, the x-axis here is not actually capacity. The x-axis does not measure a real measure of complexity. Right? The real measure of complexity is some kind of norm. And that is actually, and what's going on here is really we're minimizing some other kind of norm. And then we said, what is this norm, right? It's not, when I say norm also I should say, like about half of you are mathematicians and I'm surprised you're not really getting annoyed at me, like why am I saying it's a norm? It's not a norm, we somehow become to use this word norm, completely abuse it, right? We don't really mean, literally speaking, a norm. We mean some kind of measure of scale, right? That does not need to be, convex or homogeneous or anything, right? So what is this kind of complexity measure based on scale? And the second thing is how am I minimizing it? We're not explicitly minimizing it. And then we saw that's also something that we actually see in kind of more traditional systems. And we know we can get implicit complexity control just from the optimization algorithm. We saw, for example, that how least squares, when we optimize a least square, an underdetermined least square problem with gradient descent, we get to the minimum norm solution, and that comes just from the optimization algorithm. And so we have to ask here, what is this measure that's being minimized, and what about the algorithm is it that causes it to be minimized? Or how does our optimization algorithm, which is just gradient descent on the weights, actually minimizes some measure? And I think we really ended last time by also saying that if this is really the story here, then that means that if we change our optimization algorithm without changing the model, without changing the objective function, right? So we're not changing the landscape, we're still minimizing the exact same loss on the exact same model, but using a different optimization algorithm, maybe using different local search dynamics, as we'll see, then we're actually going to be implicitly minimizing some other complexity measure. We're going to encourage some other complexity measure to be small, which is going to change our effective complexity measure. It's going to change our inductive bias. It's going to change our entire learning rule. And we're going to get different generalization properties. And this is, I think, the slides that we maybe flashed at the last time just before lunch, just examples of this. So here we're training using two algorithms, a blue algorithm and a red algorithm. It doesn't really matter what they are. I can tell you one of them is standard SGD. Another is path SGD, which uses sort of a different local geometry given by this. It doesn't really matter. The point of this, both of these algorithms are perfectly fine optimization algorithms. What we see here is that this is the actual training objective. It's written here as cross entropy, just basically the logistic loss. And both of them reach a global minima. Or converge to a global minima of the logistic loss. How do I know it's a global minima? They reach zero loss, right? That's definitely a global minima. So both of them are perfectly fine as optimization algorithms, but what we see here is how they generalize and what's their test error. And we see that the blue algorithm is generalizing much better than the red algorithm. Okay? So in some sense, the blue algorithm is reaching a much better global minima. Now, remember, this is an undetermined system. There are many global minima, right? Because we have many more parameters than examples. And the blue algorithm is somehow finding a better one. Now, when I say better, what do I mean by better? I'm being extremely unfair to the red algorithm. Because the red algorithm is doing exactly what I told them. It's finding a global minima of the objective function, right? So it is a perfectly valid global minima. But the thing is, somehow, it's worse based on some other criteria that I didn't tell the algorithm. I didn't ask the algorithm to optimize, right? It's the way it's selecting between those global minima is like results in better generalization. It like maybe is not as good as an inductive bias for these particular problems. And we see it again, another example, a red algorithm and blue algorithm. This is SGD and Adam. And it's not so important what these algorithms are. What I'm just trying to show here is how we change the algorithm without changing anything else. And we change the generalization properties here. The red algorithm is actually a bit better in terms of optimization. It's faster. Okay, both of them are going to reach the same minima, the same value of the minima. But again, we see the blue algorithm is actually generalizing better. I mean, it's like its implicit choice of which of these global minima of this underdetermined system to choose is better. Okay, and so the story we're kind of seeing is that. The inductive bias is really determined by the bias of the optimization algorithm. So if I have, a landscape that looks something like this, that has many global minima. So if you look at, you should imagine this in like all, this is 0 and this is 0. There's lots of zeros in this landscape, and we start optimizing on some hill, right? And the question is, how does our algorithm prefer moving? So the example here, this is in this figure, it's a gradient descent and coordinate descent, two different optimization algorithms optimizing on the same objective function, and they're reaching different minima. I can tell you that if you use gradient descent, as we saw, we get to the minimum L2 norm, and if you use coordinate descent, we'll see this maybe next week, you get the approximate roughly to the minimum L1 norm solution. And these are very different inductive biases. L2 norm and L1 norm are extremely different inductive biases. Right? That can make it seems maybe you're thinking all the norms are about the same, but you should think of it in a highly high dimensional system. These two norms are extremely different. L1 in particular induces sparsity, and L2 does not. Right? And sparsity, from my perspective, is sort of the basis of much of think about deep learning. You think about deep learning in terms of we mentioned feature learning or learning features last time, and I think that's really what's going on here. So what's feature learning? So feature selection, right? If I give you a list of features, a long list of features, I give you like 1 million features, and you have to select the relevant ones. That's just sparsity, right? You want to find a predictor that's sparse and not dependent on part of the features. You can do that with L1. Now you can say that in deep learning, we want to do feature learning, right? So it's not just feature selection. It's not I give you a list of features, you want to select them. You actually want to find new features. But what's finding new features? You can think of it as just you have a continuous set of possible features, like all possible functions maybe of some form, and you want to select, to find good features in that infinite feature set. So, as long as you're not too worried about infinities, there's not really much difference between feature selection and feature learning. Right? In both cases, you want to select a few features out of a big space. Right? And again, you can do that maybe with more an L1 thing. So L1 versus L2, and you cannot, L2 never will give you anything that's sparse. Right? And so this difference can be a huge difference, and all the inductive biases coming from here is what I'm claiming. Okay, so in fact, what my view at least of deep learning, and say all inductive biases, really what are we doing in deep learning? We mentioned last time these general approximation results that deep networks can approximate any function. And we kind of dismissed them because we said, oh yeah, that's true that you can approach any function, but it's only with a huge network, so that's useless because then the capacity is too high. What actually we're seeing is maybe we are actually using networks that are really large enough to capture all functions. Okay? Because we are actually, at least they can, on the data we see, we can capture all functions, right? We can't fit any labels. So maybe we should think of deep learning really as we're optimizing over the space of all functions because our networks are deep enough. And in that case, just minimizing the empirical error with respect to all functions doesn't make any sense, right? It's really easy to optimize the empirical error with respect to all functions. I can just memorize the training data and not do anything else anywhere else, right? So I found a function that has 0 training error and is completely useless. But the thing is that that's not what we do in deep learning because we do optimize over all functions, but we optimize over all functions with a particular search dynamics. And so we will get to a function that has 0 training error, but there are many functions that have 0 training error. Right? So you should think of these as the oceans, right? Like we had before, we have like lots of oceans that are 0 level, right? And eventually we'll get to a 0 error solution. But we don't get to just some random 0 error solution. We start optimizing probably on the top of some hill or something on the ocean, and then we go down. And where are we going to get? Well, we're not going to get to the middle of the ocean. We're going to get to a beach, right? But which beach we're going to get to, right? So that determines on our optimization geometry, right? So how we optimize over the space of all functions determines, which directions we like to take in this space of all functions, and we're roughly speaking going to get maybe to a beach that's close in some sense with respect to this geometry. And this is something we're going to try to investigate in the next lectures. And then the message you should get from here is really all the inductive bias. What? To the question? Yeah, sorry.
So, from the previous slides, could it also infer that perhaps the optimization algorithm, the choice of the optimization algorithm is perhaps not as relevant. Both STD, Adam, maybe you can also use other adaptive methods, different learning rates. They have only a small difference in terms of their...
You're completely right. Hold that question and we're going to get there in 2 slides. You're completely right. So what remember your name? What Siddiq said is that I'm making this huge deal about difference between optimization algorithms, but the difference between optimization algorithms we saw here is the difference in 5.09% error and 5.35% error. I mean, that's pocket money. That's nothing compared to the difference between 5.35% error and 90% error, which is what I would have gotten here, if I just didn't optimize using a neural net at all, just chose a function that fits the training data, and that's completely right. That's the bigger picture, right? This is a smaller picture, and we'll get to that point in a second. Okay. Oops, sorry. Where was I? Okay, let's try to maybe see how this plays out, and maybe to some extent also answer Sadiq's question. And maybe this seems very crazy. Let's just see a concrete example where you exactly see this. We're optimizing over the space of all function in a way that doesn't make any sense, but just because the way we're optimizing, we're actually getting good generalization. And this is my favorite example. I've been working on metrics completion since my PhD. This is, if there's one thing I kind of sort of understand, it's maybe metrics completion, metrics factorization. So the problem in metrics completion is we have some observations from a matrix, and we want to complete the matrix to uncover the remaining observations. And you should think of this matrix as maybe some latent structure, maybe some approximate low rank structure or something like that. Okay, but how are we going to do this? So let's just optimize the optimize over all functions. So all functions here is all matrices. Formally, if you want to think of it as functions, it's functions from index pairs to entries, right? So we're just going to solve this optimization problem of optimize over all matrices the error on those observed entries. Okay, so this, some of you are looking at me strange. This doesn't make any sense. This is a completely stupid thing to do, right? Because it's very, very easy to solve this optimization problem. Okay, what's a possible solution for an optimization problem? I can complete the observed entries and put 0 everywhere else. Right, and I'll find the global minimum of this optimization problem. It has 0 value, and it'll be completely worthless, right? It will not help me complete the unobserved entries at all. The thing is, this is, again, an underdetermined system. I can also have many other global minima. I can complete the observed entries and put 7 everywhere else, or complete the observed entries and put the digits of pi everywhere else. Whatever, I can do it in a bunch of different ways. Okay, but so this optimization problem is underdetermined, completely nonsensical, doesn't make any sense. Okay, so we're going to approach it with a deep learning way. So what's a deep learning way? We have an underdetermined system that doesn't make any sense because it has too many parameters. And what we're going to do is we're going to have to do more parameters. Okay, but not only are we going to have more parameters, this is at least a convex optimization problem, right? I mean, this is super simple convex optimization problem. We're going to make it non-convex. Okay, so how are we going to do that? We're going to reparameterize x as u times v. And u times v here are full dimensional. They're unconstrained, right? So there's no, I didn't restrict my model at all, right? So any matrix x I can write as u times v. Like I can write it, for example, as x times identity or something like that, right? So this is the exact same optimization problem. All I did here is change the parameterization, okay? And so I get all the same stupid global minima, right? So I can complete, for example, take u to be the observed entries with 0 everywhere else and v to be the identity. That's one possible solution. There are many other global minima, okay? Okay, but what we're going to do now is optimize using gradient descent, okay? And so if I optimize using gradient descent, then this is what I get. So if I just optimize over, so in both cases I get 0 training error. So you don't see the training error here because it's 0. Okay, so that's okay, fine. So this is not so surprising because this problem is so easy to solve. It's like so over-parameterized, underdetermined. The fact that I can get 0 training error optimized over x is maybe less surprising. It's a tiny bit more surprising, not surprising, but it requires a bit more care that I actually get 0 training error when I optimize over u and v, because even though we know that there's a 0 error solution, right? it's a non-convex optimization problem. Who knows where our dynamics will take us, but it's not too difficult to see that gradient descent will actually find, also analytically, the gradient descent will converge to a zero solution here. The more interesting thing is what happens to the test error. So when I optimize over x, I get trivial test error. So the reason I get 70% error here is because I actually observe 30% of the entries, right? So that's just memorizing them, okay? Because basically what I'm going to do here, again, I'm going to just not complete at all the unobserved entries. But when I optimize over u and v, I actually get pretty good error. I get error just somewhere in 12% error, okay? So that's already very non-trivial error. And it seems that somehow I'm actually, the optimization somehow biases me towards better solutions that are maybe a bit more structured here. So again, I mean, there is a signal here, right? There is a approximately low rank signal, but the algorithm doesn't know it, okay? But it's somehow, sorry?
What is the relative error?
How am I measuring the relative error? So this is just, I'm just looking at the relative error just means compared to the null risk. So I normalized it so so the problem itself is not normalized. I think I relative error because I'm just looking at the squared error compared to the squared error of the null predictor. Okay? If I remember correctly. Okay. Okay, so now let's see what happens if we change the optimization algorithm. Maybe that goes a bit to that question. So this is with gradient descent with exact line search. Instead, we can do a gradient descent with very small step sizes. So that's a worse optimization algorithm and take it much longer to optimize, right? The line search actually makes things much faster. But what we see is that actually finds us a better, even better a global minima. So again, what's better? It's the same. Takes longer to find a zero objective solution, right, to find a global minima, but it generalizes better. It has, in this case, just over half the error. And this is maybe goes to the question there that the main thing we should be, we changed the optimization algorithm. This is similar maybe to the changes we had before, similar in spirit. It's not the same. And we got some improvement. Here, actually, the improvement was maybe more significant than examples before. But the big improvement we got, right, was not so much by changing the details of the optimization algorithm, but by going from here to here, okay? By doing the reparameterization, okay? Because, and this is a point we'll get to over and over, roughly what you should have in mind is the question is what is this geometry we're searching over the matrices, okay? And the details of optimization algorithm do have an effect on that, but the bigger effect here is the reparameterization, which could completely change the entire search geometry. So that hopefully answers. And again, we'll get to that point even just today several more times. Okay, so what's going on here? In this case, we can sort of maybe understand what's going on. We don't have a complete understanding yet, but what we initially proposed, and this is based on some empirical evidence, it seems that we're generally finding if in least square problems, gradient descent is converging to a low Euclidean norm solution. Here we're sort of converging to a low nuclear norm solution, and so again we can kind of identify. This is what we can sort of do is identify the nuclear norm as the relevant complexity measure here that the algorithm on one hand is minimizing, and then if the nuclear norm is small, or the trace norm, just the sum of the singular values, then we know how to get why this is good inductive bias. We know we have an approximate low rank metrics. Then actually minimizing the nuclear norm can give you good generalization that we knew from before. This is proved rigorously in some cases. It turns out to not always be the case, and again, we might get back to this next week. I'm not sure. The details here are less important. I just want to get the picture. We'll get towards the end of the lecture today, or the second half of the lecture, we'll start getting more into details. A few more examples I just want to flash, and really I'm just going to flash them. We're going to get into the details next week.
Over here, if we have, let's say, a couple more matrices like U, V, W, Z, and
right.
If we minimize like that, does it go further?
Excellent question. So we'll look at that specifically next week. I can already tell you that we don't. So one, we don't know the answer. That's a question of active research. To some extent, there's some. It doesn't. Okay, it depends on the loss function. With the squared loss, it's not going to make a big difference, which is maybe surprising. We expected it would, but when we kind of understand it analytically, it does make smaller differences. But we're going to get exactly to that, and we'll actually see an example, a similar example in like 3 seconds. Okay, or yes. right?
Like, can we actually figure out
Okay, okay, so that's a good question. So the question here is, what I showed you here is you have we started with an algorithm, right? We said, let's do gradient descent on U and V and figure out what is the implicit bias, okay? And the question that, remind me, that Yatin is asking is, can I go the other way? Can I start an implicit bias and then design an algorithm and give it to me? So I have three answers. One is you shouldn't do that. Why? Like, if you have an implicit bias that you want, you might as well put it directly and just use it as a regularizer, okay? So that's maybe one answer. Rather, what we're doing here is we have what we're trying to do in this, the entire endeavor here is we have a method that works, gradient descent on deep neural networks, right? Undoubtedly, just empirically, we see it works, and we're trying to understand what's going on there. So so that's kind of the question we want to answer. But that said, we do have some recent work where we did try to answer that question of, I have some implicit bias, how do I design a network that gives me that implicit bias? Okay, so for example, I want my implicit bias is some kind of group norm or some kind of, something else. Can I design a network that has that specific implicit bias? And you can do that. That's actually a fun exercise. It's more than an exercise. So first of all, it's kind of a nice puzzle. The question is, what is the value of it? I don't think it has, it doesn't have, I don't think it ever, it's something you'd really start an implicit bias and design a network. We did that both just to help us, what we want to do is develop this mapping between optimization algorithm and implicit bias. So mostly we want to go this way, but just as an intellectual exercise, going the other way is helpful for developing tools and intuitions. That's the main reason we did this. Another reason is maybe you want to just understand how you can, maybe it's not that you have exact implicit bias, but you want to say, if you want to get more sparsity, or I want to get more correlation, less correlation, I don't know, something like that, then I have a system that has an implicit bias that I don't understand, like deep neural networks, and I want to make it more something. And so then I just want to know how to tweak it, like what tweaks to the architecture will make it more like what I want. Right? So that maybe makes sense. Okay? Okay, let's continue with just flashing some more slides here. So I just want to see a few more examples where we're optimizing over all functions and getting very rich in inductive bias. So if you train a single unit, I guess I didn't mention it last time, we'll look at this analytically next week. If I train a single unit with gradient descent with the logistic loss, I converge to the max margin separator, the hard margin SVM solution, okay, so which has an implicit L2 norm embedded in it in SVM. Yes? Here this is regardless of serialization. Yeah, so I didn't go over, I thought I would do it last time, but I didn't have time, so I didn't go over details. So this is regardless of initialization. We'll go over this result specifically, we'll go over very carefully next week, okay? But for now, what you have is a single unit, I just get L2. This is just gradient descent in a linear model, roughly speaking. Now you can ask what happens if I have a deeper network. And let's just stick now to linear networks. Okay, so all the units here have linear activations. So every unit is a linear function of its input, so it's a linear function of the entire input. So really this entire network is just computing a linear function. So this is in some sense not like something that makes too much sense because this is, it's a ridiculous parameterization for a linear function. Okay? But as we said, I mean, it's like the metrics factorization, maybe it does make sense because changing the way we parameterize our functions, in this case all functions is all linear functions, and changing how we parameterize them even in this ridiculous way might actually change the inductive bias. Okay? So we have this parameter, you can think of this as just a parameterization of linear functions beta, and the question is if I do gradient descent over the weights, what kind of beta will it be biased to, what kind of linear predictor? And the answer, quite boring, is the same. There's no actually change in inductive bias here, but things get a bit more interesting when we look at linear convolutional networks. Okay? So linear convolutional networks, each layer, I think, each layer implements a convolution on the previous layer. So here I just wrote it as 1D cyclic convolutions. So I have, for each layer, I have a single vector of weights, and each unit has the same weights rotated by 1. Okay, and the last layer is fully connected. And again, all the activations here are linear. So all that's going on here is I'm just implementing a linear function from the input to the output. This is just a strange reparameterization of a linear function. And now I can ask, what happens if I train the weights of this linear convolutional network with gradient descent? So again, the model itself doesn't impose any bias. It represents all functions. Right? There's no, absolutely no inductive bias coming from the model itself. But if I train this with gradient descent, then what I actually get is I'm implicitly minimizing the L1 norm in the frequency domain. Right, so I'm getting a linear of all, there are many different linear predictors that separate the data here because I'm underdetermined. And the linear predictor I'm going to choose is the one that has the minimum, such that its Fourier transform, its discrete Fourier transform is the minimum L1 norm. So I get sort of sparsity in the frequency domain. So this is with a single hidden layer, right? So it's single convolution. If I go deeper and I have, this to some extent, answers, goes towards answering what happens if I have multiple layers, how does this change? And in this case, we know analytically how it changes. And again, we'll look at all these results, or basically these results next week and see how they're derived. If I have more layers, I get this bridge penalty quasi-norm in the frequency domain. So if I have 10 layers, I get the 0.2 quasi-norm, right? So this is just clear. Maybe if you haven't seen this before, right? So this is just you can write an LP norm of W, right? The sum of W to the P, right? And they can just take this with P less than 1. I mean, it's not going to be a norm, but it's formally defined, right? And this is even more sparsity inducing than the L1 norm, right? So the picture is something like this, right? With a fully connected network, I'm not biasing towards sparsity in the frequency domain. As I go deeper and deeper, I get more what I'm showing you here is the linear transformation learned by the coefficients of linear transformation learned by the network. I get more and more sparsity in the frequency domain. Okay. Okay. So what we've seen here is already two examples where I'm optimizing over the set of all functions, and all my inductive bias is coming from how am I searching over that space, okay, the geometry of that space. The first all functions were all matrices, and the second all functions were all linear functions. But let's really talk about all functions. So how I can represent all functions. So a ReLU network, now we have to introduce nonlinearities. We want to talk about nonlinear functions. So a ReLU network, even with a single hidden layer ReLU network, can approximate arbitrary functions, right, if I let the network be wide enough. So let's learn using infinite width ReLU networks, right? So I have infinitely many ReLU networks. With that, I can approximate or approach, depending on what your formalism for infinite units, arbitrary functions. And now again, I'm going to train with gradient descent. So I'm optimizing over the space of all functions. But if I train this infinite width ReLU network with gradient descent, which of these all functions am I going to converge to? What am I actually kind of minimizing? So let's start with univariate functions. So at least for, do I have it here? Yeah. At least for univariate functions, that's I mean a single input unit, infinite ReLU units, and then single output unit. So I'm just learning functions from R to R, right? So I have, right? So this is, it seems silly to have a single input unit, but even that, right? I have a bunch of points, right? This is the input, this is the output, and I'm going to interpolate them, but there are many ways of interpolating, right? Am I going to go like this, right? Or am I going to go like this? Or am I going to go maybe more smoothly? I don't know. Okay? So the answer is that what I'm going to do is from all the functions interpolated data, I'm going to choose the one that minimizes, roughly speaking, the second order total variation, the integral of the absolute value of the second derivative of a function. Okay, so this makes sense, right? And this is kind of a smoothness inducing penalty. I want my interpolant to be smooth in this specific way. This is something that, if you wanted to interpolate data, and to choose some penalty for your function, this would be a very a very sensible penalty to choose. But the thing is, we didn't choose it, right? All we said was optimize over the space of all functions, representing them using one hidden layer ReLU network. Okay? And this choice came to us completely just from the fact that we're doing gradient descent in this parameterization. Okay? So this is for univariate functions. We can extend the result also to multivariate functions. The exact statement becomes a bit more delicate. I'm not going to say here. Roughly speaking, what we have is, again, higher order derivatives. So we actually have to look at the derivative of the Rudin transform of the function. And to be more formal, we have to actually look at iterated Laplacians, iterate half the times inside the transform and half outside. The details here are not so important. The point is that we get some kind of sensible smoothness penalty. Okay? This is one hidden layer.
And does it depend on things like the learning rate, the initialization?
So as I stated here, this result is rigorous for, does it say here? Okay. This result is rigorous for logistic loss. And for logistic loss, it doesn't depend on pretty much anything. So any initialization and any learning rate. For squared loss, we think we get something similar, but and it would depend on all these things, and we don't know how to analyze it exactly.
This is classification.
This is for classification. All the results on this page are exact and rigorous just for classification. So yeah, yes. So it doesn't matter. For classification, it really doesn't matter. Pretty much anything you do. So if you want a specific result, so you initialize any non-degenerate, you have to initialize in a non-degenerate point and do a gradient descent with a reasonable step size. Just want the step size such that it would actually converge. Or actually go to zero error. Yes?
Should I think of the infinite width limit as truly infinite width, so H is really smooth, or it's just that minimizing that norm means that I have to have less kinks?
Okay, so the infinite, okay, wait, so there's separate, so let's unpack, okay. So first of all, how to think of infinite width, it wasn't super formal here. So there are two ways, there are multiple ways to think about it. One way is, this is like the computer science way from my perspective. There's no such thing as infinity, right? We can just write. So just think of networks with a large number of units. And first of all, look for every number of units n, what's the limit, what function you get to, and then take n to infinity and see what you'd converge to. And you'd converge to the function minimizing this. So that's one way to think about it. Another way to think about it is when we can talk exactly about infinite width with, so the other way to think about it is basically as a mean field approximation. So you can think of infinite width as an integral over units, and then you can think of it using the dynamics in this mean field approximation. So the gradient descent dynamics become Wasserstein gradient flow, and I think maybe, is Francis going to talk about that, or is Andrea, somebody? Maybe? I'm not going to talk about that. Maybe some of you are familiar with that. So that's another formalism that you can take here, and either of them work. Okay. The other thing we said with the kinks, it's true that, so it's not the case that, so it's actually more subtle than that. It's true that you can have a function with a small number of kinks that minimizes this norm. But not all functions that minimize this norm have a small number of kinks. You actually have completely smooth functions. Right, so you can have a piecewise linear function and minimize it. So one of the minimizers of this, right? There are many minimizers of this. One of them, in fact, is piecewise linear and has a small number of kinks. When we actually train the network, the dynamics will not take you to that. It'll take you, with a large number of units, it'll actually take you to a smooth function that minimizes this. So it's different than saying you're minimizing the kinks. Okay, I hope that, yeah. I'm sorry for the rest of you that don't necessarily know what we're talking, and okay, we can, if you're interested, ask later, yes.
What is this D+1 derivative of radon?
So think of it as a higher order derivatives of the function. So it's not, I mean, do I have an intuition for what, and again, it's some kind of smoothness penalty. That looks at like how, instead of, so I don't actually think this, so I have to say that in one dimension this is very compelling. In higher dimensions, regularizing these very high order derivatives, I'm not sure it completely makes sense. Like from a modeling perspective, not, what I actually, so this is actually a question, the question is what happens here with deeper networks, and I suspect that with deeper networks, but I don't know. I mean, I would love to understand. The exact same question is well defined if you have deeper networks. Again, you have a depth 2 infinite, both the layers are infinite width. Depth 2, this is completely well defined. I can write the limits. I have no idea how, what it converges to. And I suspect that you get regularization on lower order derivatives, but I don't know. And that would make more sense. Yes?
So instead of looking at the implicit bias in the function space, are there works that have explored sort of the implicit bias in the joint space of the output and the features, so that we
not sure what you mean by features.
The output applications that are learned, so that we also have an understanding of like what features are learned.
so you can, yeah, I guess the short answer is yes, people looked at that, but I mean, that's not the view I'm taking here, right? Okay, but okay, so let's, yeah.
So one quick question over there. Like,
Sorry.
this implicitly minimizing this thing, couldn't we maybe check or maybe ask if at initialization itself, the parameterization and this infinite width is lending itself into a function which, although is not interpolating right now, but is already smooth?
That's not actually, well, smooth. It's going to be actually the initialization here in some sense, depending on how you do it, is going to be the constant zero function. So if in order to get this to work for least squares, which is we don't understand rigorously, you'd have to initialize essentially to a tiny fluctuation around the constant zero function. So sure, it's very smooth, right? But I don't think that it's smooth not in respect only to this, with respect to anything. And the question is how do you go away from it? Like what kind of so yeah, so you're right that the way this is going to work, and this makes sense, is you're going to start from something. Okay, but this fits the general picture. It's not that you're going to start from something very complex and gradually minimize your complexity. Okay? What's going to happen here? So think about least squares. That's you minimize an undetermined least square with gradient descent. You start from the most simple solution, which is zero. Right? You start at the origin, so you start with zero complexity. And what's going to happen is, over the course of optimization, you're gradually going to increase the complexity. You're going to go away from the origin and look for, and search for your zero error solution. Okay? It's not true that the complexity is going to be monotonically increasing, but roughly speaking, it's going to be increasing as you go. Okay? And in fact, for least squares, in some sense, it may be, in some average sense, it even is monotonically increasing. But it's not going to suddenly go up and then go down, and right. So you're kind of trying to go to a solution that to zero solution that requires you to travel the least. So to increase the complexity the least. But the question is, what is this? Still, the question is, what is this complexity that you're gradually increasing? Okay, and that's roughly also what's happening here. Okay. 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 And then again, to answer this excellent question, what we're seeing here really is the game here is that we have, we really want to understand what happens in space of functions. I'm telling you we're optimizing overall functions, but we're actually looking at a particular parameterization. And the real reason we're getting these super rich inductive biases is we are starting from some kind of bias in parameter space. But this bias is probably relatively simple. We don't know exactly how to characterize, and it's not like gradient descent has L2 bias in parameter space only when you're minimizing a least square problem, right? So when you go beyond that, it's not exactly L2, but it's probably still a relatively kind of simple bias. And it's actually, we'll see later, in some cases maybe it is exactly L2. But the thing is that what we care about is not what happens in parameter space, it's what happens in function space. So even if we have think of this as a sublevel set of our complexity in parameter space is kind of very simple. Once we map it to function space, we get something that can be very, very rich. Okay? So in some sense, and this directly answers the question asked before, that when I say that the optimization algorithm controls our inductive bias, it's still a large part of that optimization problem is the architecture. So it's not what you should get from this. If I said before that we're optimizing over the set of all functions, the model class itself is completely irrelevant, doesn't give you anything, that's true because the model class, as a hypothesis class, is the class of functions you can get is all functions. But the architecture is very important. The thing is that the architecture, the kind of classical view is the architecture is important because the architecture limits what functions you can get. And that's not the case here. But the architecture rather is important because the architecture determines the mapping from parameter space to function space and is the biggest contributor to the geometry by which you're searching in function space. Okay? So that's the biggest contributor. And that maybe is the difference, as we said before, because between 90% error and 5% error. Okay? Another thing that's definitely important is what is the search, what's the geometry of the search in parameter space? Okay? Is it, for example, more like an L2 search or an L1 search? That is still very important because I said parameter space is high dimensional, so there's a huge difference between local geometries. Okay? And the thing that still is important, but probably the least so, is the specific optimization choices. Like, are we taking big step sizes or small step size? Are we doing, I don't know, like all these choices like that are probably the least important because they only change it a bit, like, the details of this geometry and parameter space. Okay, but nevertheless, we want to try to understand how they affect things.
Nati,
Yes.
So if in the space of function I look at like the norm that was minimized
Yeah.
implicitly, if I say I only look at all the functions bounded by some
Yeah.
value, does that give me some kind of convex set in the space of functions?
It will not be convex in the space of functions. So right. So the question you're answering is an excellent question, which we looked at. Suppose we actually know what happens in parameter space. Suppose we just have L2 in parameter space, the simplest possible thing. Then we can ask, what is this? What's the complexity measure induced in function space? Okay. In particular, I can look at it two ways. Just thinking of that. What is the complexity measure? So we call this a representational cost. So this is, we write it here. I was planning on getting into it later on, but. So this is an important concept here. So representational cost of a function, is fine, is just the minimum way of suppose I actually know what I'm thinking of the norm of W as the cost in parameter space. It's the minimum, the cheapest way of actually representing it using my model. Okay. And you can look at this, or you can look at sub-level sets, like in this picture, right? If I have a unit, a ball in parameter space, what does it map to in function space? And this can be highly non-convex. Okay, so in particular for this, even example we saw for deep convolutional networks beyond depth 2, so depth 10 convolutional networks, if this is L2, then this would be the 0.2 quasi-norm, which is non-convex. Okay, so this can definitely become non-convex. Okay, so in fact, so in all the examples we saw before, in fact, yeah.
So I wanted to ask about the plot. What you're trying to say
This
is
plot?
That, yeah.
Yeah.
Is that many functions map to the same W?
Not so much the many functions. No. Well, that's definitely not the case. Each W maps to a single function, right?
Yeah.
So it's just that this mapping is a like very complex mapping. And so it can map something that looks simple to something that, like, in particular, can map like a convex object to a convex ball to a non-convex ball. Okay, the mapping is also okay. So definitely every W maps to a single F. There are many F that so a single F can be represented by multiple W's, which is an issue we're not talking about here. But this was just supposed to represent the fact that this mapping is complex, is complicated. Okay. 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 So in fact, in all the examples we had here, and this goes back to I think many of the questions you asked, in all these examples, I actually can get the same thing, not with implicit regularization. I can get the same thing if I just look at the minimum Euclidean norm on the weight, so minimum L2 norm on the weights under the parameterization we get there. Okay, so if I look at the minimum Euclidean norm and the matrices, so it's like minimum Frobenius norm subject to getting to fitting the data, or for the linear convolutional networks, I get the same thing if I regularize the Euclidean norm of the weights, and also here. And so it seems that everything in these examples, at least, everything is coming just the complexity control in parameter space is very simple. It's just like L2. Okay? And everything is coming just from this parameterization. So in fact, you can ask, maybe all this discussion of implicit bias, it really, okay, fine. It's still important to understand that we have implicit bias coming from the algorithm, because not in having explicit regularization, maybe we don't have to study it so carefully, because maybe it's just L2 in parameter space, and everything is coming just from the parameterization. And the answer is complex. So in some sense, as we'll see next week, you can get some asymptotic results that say that in some asymptotic sense, for some restricted class of models with a logistic loss, this is actually correct. I mean, you always would get L2, but we'll also see how in many cases that's not the case, and not the case and very important, and you'll get something that's extremely different. So that would be the case either when you're using a loss like the squared loss, or even if you're using the logistic loss, but you're looking at things non-asymptotically. And we'll also argue that these asymptotic results are in some sense can be a bit misleading. Okay. Let me actually skip this slide because I do want to get to some new material. Okay, so let's go back to this plot. Okay, so actually, Okay, that I did skip. Okay, I still don't want to talk about that slide. So, I mean, so this is, so let's go back to this plot now. Now we understand both why we're not over fitting here, like because we have some kind of complexity control, and this complexity control comes from the algorithm. And the main question that this leads to ask is, what is this complexity control? But there's another thing actually that's going on here that we didn't talk about so far. And it's actually not too difficult to understand. So we understood why we actually get good generalization even over here, even when the network is very, very big. But why is it that this actually goes down, right? So we said this what is this x-axis? This x-axis is not complexity. Complexity is something else, some kind of norm-based complexity probably. Why is it though that the test error continues decreasing here, even though we're not fitting the data better, right? So the fit to the data is not improving. Can we understand why is this going down? And I would say yes, and that's actually, we can see that again even with classical learning linear methods or kernel methods. It's really just linear methods with SVM. So let's just think of what happens when I train a hard margin SVM or kernel ridge regression, if you prefer, with some universal kernel like the Gaussian kernel. So the Gaussian kernel is an infinite dimensional, corresponds to infinite dimensional feature space. And so I can actually, in this infinite dimensional feature space, I can represent any function. I can always fit the labels, right? So if I do a hard margin Gaussian kernel SVM for classification, I can always, the data is always separable. Any labels are separable, okay? But now let's think of what happens if instead of using the exact Gaussian kernel, I use some finite approximation of this Gaussian kernel. Right, so for example, I use these random Fourier features or Hemian rect features. I define here, and the thing is that if as the number of features goes to infinity, I'm going to approach my Gaussian kernel. But for any d, so think of the x-axis here roughly is corresponding to the number of the dimensionality of approximation of my Gaussian kernel, or the number of random features I'm going to use. Okay? I'm going to get better and better approximations for the Gaussian kernel. So what's going to happen here? Once I have more features than data points, okay, I'm high enough dimension, I can always get zero training error. But I'm not going to do it with the Gaussian kernel, right? I'm going to do it with some approximation for the Gaussian kernel. As I have more and more features, I'm going to approximate the Gaussian kernel better and better and better. If what I think is the Gaussian kernel really is my correct, the RKHS norm under the norm induced by the Gaussian kernel is my good measure of complexity, then as d goes to infinity, I'm going to approximate it better and better. So I'm going to get a better, I'm going to minimize the complexity measure that becomes a better approximation of what I really want, right? And so I'm going to get exactly this type of behavior. That as the dimensionality increases, and I'm talking about this Gaussian, this finite approximation of the Gaussian kernel situation, as my dimensionalities and random features increase, I'm always going to get zero training error, but my test error is going to improve because the complexity measure I'm actually minimizing is going to be a better approximation for the real complexity measure. Okay? And what I'm arguing is we see here a similar thing. So if you're less familiar with less comfortable with thinking about the Gaussian kernel and random feature approximation of the Gaussian kernel, maybe another example you can think about it, which is maybe a slightly less direct but captures the same essence, is from metrics factorization. Again, so that's my favorite example for everything. So think about doing metrics completion. Now we're doing explicit regularization. There's nothing implicit here. And what we're going to do, our learning rule is going to be, is my learning rule not there? Oh, it is blur. Okay. No, okay. So my learning rule is going to be, I'm going to look at the minimum nuclear norm metrics, but I'm going to limit, and I do think the nuclear norm is a good complexity measure here, but because of computational reasons, my metric x is very large. So imagine I'm working on something like the Netflix data, and the metrics x is like 10 million by 100,000. I cannot represent the metrics x explicitly, so I'm actually going to store a low rank approximation of x. I'm going to store x as u times v, and now u and v are dimensionality D. So my whole system is constrained to be dimensionality D. Now, I'm not limiting my rank here for complexity control. I do think that the right thing here, the best model here, is actually an infinite dimensional low nuclear norm solution. Because, for example, maybe I think that it's not there's a small number of factors in data, but there's like many factors of, I do think that to expect a metrics with like decreasing spectrum. But just for complexity reasons, I'm limiting my rank. And what we see here, and you see this empirically, is as I increase the rank, my test error becomes better and better and better. Again, because of the same reason. Because as I increase my rank, I'm actually getting closer to really what I really want, which is a full rank low nuclear norm matrix. Okay? So in both of these cases, you see that what's on the x-axis is not a complexity control. What's on the x-axis is some kind of dimensionality of the approximation to our infinite dimensional system. Okay? And I would argue that that's really what's happening in neural networks also. That the real object that we should be learning with is an infinite size network. Okay? The thing is that, how do we represent an infinite size network? Well, it's the same way how do we represent a real number. Like how do we represent a real number in the computer? And we can represent a real number in the computer. We represent some kind of truncated finite precision approximation of it. In the same way here, we can represent an infinite dimensional network, an infinite size network. We represent some kind of truncated finite representation of it. Right? As our truncation becomes finer and finer, the representation will be better. Okay? And that's kind of what we're seeing here. And what we want in some sense is to work, when we will do real numbers, we try to work with enough bits of precision that we can just think of the real, arithmetic over the real, or our real numbers as the model of what's going on. And similarly here, our goal kind of in deep learning, we see that as we increase the size, things are getting better and better. We want the size to be so big that we're essentially have a good approximation of the infinite size model. In particular, what we see here is that our methods generally do not and really should not rely on this on the size of this approximation being small. In the same sense that if you're programming a numerical library, for doing you're implementing some numerical routines, so you're not using really with reals, right? You are actually using floating point numbers or something, some truncated approximation for the reals. Okay, and then if your system relies on this truncation to work well, you're in trouble. So in some sense, if you program me a system that worked with 32-bit reals, but when I went to 64-bit reals, suddenly it'll stop working, that's really strange, right? You wouldn't expect your algorithm, if you have an algorithm that only works when you use low precision real numbers, but doesn't work with higher precision real numbers, your algorithm is messed up. It's not a correct algorithm, right? And in fact, when you analyze the numerical algorithm in a second, what you usually do is you first think about it, what happens if I work over the reals, and try to understand it over the reals, and make sure that it's correct over the reals. And then you also have to make sure that it's actually numerically stable, that if you use low precision arithmetic, or bounded precision arithmetic, things will also work well. But you don't start by analyzing with a low precision arithmetic and then relying on that. And that's how I would argue and how we should also analyze neural networks. We should start by understanding their infinite size, and then maybe also worry about how big do we need to be in order to be infinite. Yeah, question?
So, on one level what you're saying makes sense, but what about those examples where one actually takes some teacher neural network, so the ground truth function is actually representable by some small neural network, there is no problem there. And even despite that, taking the neural network larger is actually computationally advantageous. So what does that mean?
Okay, that's an excellent question. Well, the short answer is I don't know. But so Lenga's answer is like what I said. These examples make sense because in these answers, the ground truth, right, was high dimensional. And what Lenka is saying, even in examples when I know the ground truth is low dimensional because I actually planted it that way, then I still benefit by higher dimensions. So I don't actually know exactly the answer, but what I feel is the answer, right, is that it's still the search in the optimization, the search in some sense does become easier in some sense in higher dimensions. And so the complexity, we have to acknowledge that we're minimizing. We're not, okay, maybe to answer that I'll say, and I don't know if that was an answer to that question or another question. Okay, so maybe my best answer to that, which I don't have really any really good answer, is that when we say that we do ERM, right, we minimize the loss, we don't actually minimize the loss. We use a specific algorithm. We do local search using some dynamics. Okay, and the thing is, this local search using these dynamics is not the same as argmin, and it's not the same for two reasons. One reason is because it's actually stronger than argmin because it finds a particular minima, not just any minima. The second reason is that it's also weaker than argmin because it might not find the minima. Okay, and so in my view, it's minimizing some. It's it's minimizing this minimizing this complexity. And I kind of, when I increase I need the dimensionality to be large enough for this dynamics to work. But really, I don't know. I'm starting to repeat myself because I'm not.
The matrix completion is actually a good example, at least in some of the
You can see, yeah.
that people study.
You can see that, yeah. Right. So in matrix completion, also for matrix completion, even if your metrics, so there we can exactly see it. So matrix completion, if you restrict to rank which is exactly the rank of the planted solution, you might get stuck in local minima. Once you increase the rank, then you don't get stuck in this local minima. Okay? But there it would be, you'd only need to increase it by a, okay, so theoretically we know there is by a bit, but empirically it does seem to increasing it by a bit more than a bit, by 10, increasing the rank by like 10 or so seems to be sufficient. It's not like this decaying effect. But yeah, but it's something like that. Question there? Yeah.
I have a question to the comments.
Yeah.
What you think about it. So I think that, so what you're saying is that so the error goes down because you decrease the filtration around the good solution, but at the same time, so when you increase the number of hidden units, you could also change actually let's say the kind of function that which you are going. So just to give you an example. So imagine, so if I take very over parameters limit, I get 10 decay. But actually, if I don't take so many units, I will do more rich.
Okay.
So it's true that the error will be higher because I have the situation, but around the solution, which is actually better.
Okay. So right.
Somehow there is also this.
Okay. Okay. So we'll get to that. That's one of. I do want to get to that next week explicitly about that. And that's in challenge. And okay. So what? So the comment was that sometimes I actually maybe I'll rephrase the comment a bit. Sometimes the infinite width limit might be very different than a finite approximation in a significant way. Okay, and so this is how kind of I'll take the comment, and that's indeed something we're trying to understand. So specifically, the results, it says that if you take an infinite width limit in a particular way, you're going to get this degenerate regime, the NTK or kernel regime, which is, from my perspective, degenerate because it doesn't allow you to get any rich bias. You're stuck with just linear methods. And the question is the failure here because really we need to take this infinite, so I see this as just saying that this whole story was maybe wrong, that the infinite width, no, not this whole story, but this last part of the story, that taking an infinite, viewing things as infinite, as a finite approximation to infinite is not the right way to go about it. That's possible. My more answer to that is depends how you take this this limit. It really depends on the details of the limit, and you can take this limit in a way that it's meaningful. Okay? And now there's a question in the systems that when you see deep learning is working with a large network, it's a bit difficult to say what is the limit that it's getting to because we only see one point, right? But I think that my solution, which I'll describe in detail next week, is exactly how we can take the width to infinity and still, like, in a meaningful way, in a way that we don't get the kernel limit. Okay. Okay. Yeah.
Just one quick question.
Sure.
This explanation on this image, wouldn't it be incomplete if you think in regards to double descent?
Excellent. Okay, excellent question. That leads me exactly to my next topic. Okay, so there's one thing that doesn't fit our understanding. Okay, and this is something that I have to say we were completely blind to for many years, even though it was in front of our eyes, and really was pointed out only fairly recently by Misha Belkin, only like 4 years ago. So the one thing here that doesn't really fit is that we're getting good generalization even though we're insisting on a zero training error solution in situations, in noisy situations. So in a situation where approximation error is non-zero, right? So in particular, in terms of, we said that this is the plot we should always have in mind when we're doing learning theory. We want to balance complexity and complexity here and training error here. So we want to be somewhere on this regularization frontier, probably somewhere in here. But the solutions we're finding with this, even if you buy all the story about implicit regularization, they're the minimum complexity zero error solutions. Right, so minimum complexity zero error is in the extreme point of here, at this point. So these are the solutions, and this seems to be and we're seeing this even in cases where we are in noisy situations, and we'd expect to be, over here, the error is like, the training error is like, or the test error is like 15, 10%, something like that, so fairly noisy situations. And in these cases, we wouldn't expect to be here, we'd expect to balance things. Okay, so maybe to understand this a bit better, let's go back to, probably you've seen something like this in some kind of machine learning or data fitting class. You have some noisy data and you want to fit it. My training data is the red points, and I can fit it with models of different complexity. Like here, complexity would be degree of the polynomial. I think the simplest complexity measure. With degree 0 polynomial, you get a pretty bad fit. With a degree 1 polynomial, it's still pretty bad. With degree 2 polynomial, you get a better fit. You're still not, getting zero test error, zero training error. I can increase the degree and decrease the training error, and then to get zero training error here, I'd have to go to degree 9. Okay, and what happens here, I'm fitting the data. In fact, I'm overfitting. Why I'm saying I'm overfitting? Because I'm fitting the noise at this point. It's pretty clear that what I'm doing here is just with my degree 9 polynomial is just fitting the noise, and because of that, I'm getting bad generalization. And so we see classic U-shaped curves like this. So the important curve here is the red curve, is the test error. Here, here as I'm increasing complexity, here I'm underfitting. I don't have enough complexity in my class to fit the data. So I'm fitting the data, as I increase complexity, I'm fitting the data better and better and better and better. Okay? And then at some point, I start overfitting. So I'm starting fitting the noise. So I'm going to define kind of overfitting as fitting the noise. And in that point, my test error starts becoming worse and worse because my estimation error is increasing. Estimation error, my capacity becomes too high, right? And so this term starts dominating. Okay? And so the classic understanding is that we want to choose a point like on the bottom of this U curve somewhere here. And the conventional wisdom, as expressed in numerous machine learning books and classes, is that we should never insist on zero training error. That a model with zero training error probably will generalize poorly. Okay, and yet what we're seeing, right? So we should be somewhere over here, right? So this axis roughly corresponds to this curve. We should be somewhere over here, not over here. And what we're seeing is we're actually getting good generalization, even if we're way over here, right? Over here rather, okay? And this has been mostly, so the first paper that kind of put on the table by Misha Belkin and co-authors, this actually, Misha already before talked about this, but this is this double descent curve paper that, I'm curious, how many people have seen this figure before? Double descent, okay. Everybody, excellent, okay. So let's try to understand what's going on here, because I think that 95% of this we understand completely and has nothing to do with this phenomenon we just saw. So, okay, this is the classic curve, right? And what we're seeing is this behavior, it's double descent. So let's look at the double descent. Why are we getting this double descent, okay? So first of all, let's try to understand what are we plotting here, okay? So what are the axes, okay? Okay, great. So the x-axis is dimensionality. So this is a cartoon, but you get similar things, and you can think about it. What you should have in mind is this least square problem in dimensionality d. So d is dimensionality in a fixed number of training examples, okay? So the x-axis dimensionality, here is the error, but the error of what? Okay, so the error of the minimum, the error of the ERM solution, the minimum squared error solution. Okay, but what does that mean, minimum squared error solution? We just said that just saying argument is not enough. You really have to say about what algorithm did you use to get it. Okay, and the algorithm. Okay, so what algorithm you used? The algorithm we're promoting is like maybe what you did was gradient descent in the loss. The way this was generated was probably not with the gradient descent. Like if but rather like if I give you now some data and I ask you, find the least square solution, like what would you do? Okay, what you do is probably open up, I don't know, either MATLAB or Python, or I don't know what you use, and type in something like this, right? So use the MATLAB backslash or the Python least square. The thing is that any of these three learning rules, they're not really one learning rule. each of them actually does one of two separate things. And you can see that very explicitly in the documentation. If you open the documentation for the backslash or least square, what it tells you is the following. It says, if the problem is overdetermined, finds the solution, what I call here W, finds a solution W, then minimizes the residual, minimizes reconstruction error. So this is what's going on here. You're actually exactly minimizing the error. But the documentation also tell you that if the problem is underdetermined, okay, then finds the minimum Euclidean norm solution to the system. Okay, and that's also what we saw that we find with gradient descent. Okay, so what happens over here, this is the line of whether the problem is underdetermined or overdetermined, this interpolation solution. What we're seeing is we're using actually, even though the same piece of code actually executes one of two completely different learning rules, right? Either it minimizes the loss and doesn't care at all about the norm, or it insists on zero solution and minimizes the norm. Okay? And so this in some sense, and now we really should understand each of these learning rules separately. So over here, just a second. So over here, in this part, in the undetermined part, we understand. This is the standard U curve that we saw, right? There's nothing to do with here with norm. The complexity control is really dimensionality. The x-axis is really complexity control, right? There's really complexity, and then we get the standard U curve. Okay. What we should focus here is really what happens here. And what happens here is that now the x-axis is not actually complexity control. Right? We said the complexity control actually comes from the norm. The x-axis is the degree of approximation. Okay, that has nothing to do with complexity, and we understand. We just talked about before why it's maybe not surprising that we get an improvement. Things improve as the approximation becomes better because we're just not plotting complexity. Okay, so this is exactly kind of the same decrease that we saw before. Now I'll take the question. Yeah.
Shouldn't the x-axis have some relation to the number of samples you have?
So this plot is for a fixed number of samples. Okay, so you should think of it, really you should, if you want to take it more symptomatically, think of the x-axis as the ratio of dimensions to samples. Okay, and this would be 1 over here. Okay, okay, so this we actually understand. And actually, if we look at it, we actually got similar plots also before. So this is the same plot. I think this is the plot I started with. I only showed you the blue plot. The blue plot is what you get without regularization. And just, I mean, I'm saying that this is actually in front of our eyes, but we missed it, right? You can also already see here a kind of double descent. Now, it's not as extreme because the network is more complex. It's actually harder. The reason this peak is not as high because it's much harder to interpolate in some sense. It's numerically difficult to solve this interpolation problem when you're right on the edge here. Oops. Whoa. Go back. Okay, but we see that we see it also here, and even going as far back as 98, an explanation of boosting. I don't know how many are familiar with this plot. You can kind of see sort of a double descent also there. We completely missed this, and it took several years for Misha to kind of point this out and notice this. But again, the actual fact that we get an increase and decrease is not surprising. What is surprising is the fact that this work with a zero error solution, even though we're in a noisy case. And this is really, I think, the main thing that Misha pointed out that is like shattering. That even in many noisy cases, in cases where the error doesn't go to zero, we can get a good generalization with this, what I call minimum description length learning rule, like minimizing the complexity subject to zero error. Okay, and just to see that, yeah.
I mean, weren't there other works for kind of fitting MNIST, which intrinsically is noisy? You don't go to zero test error. People have seen this double descent, so I feel
what do you mean by
uneasy that you're like.
Misha? Okay, what do you mean by seeing the double descent? I mean, there are plots. If you look back, they have that. But people, as far as I know, there's no previous work that definitely the term double descent. No, but I think there's no work that pointed out. So I think there are two parts here. One part is the double descent. So I would separate here, and this is maybe the point I'm trying to make, between two things. One is the fact that we see a descent, the double descent itself. We see a descent here, and the descent itself is not new and is not surprising. And yes, many people, I mean, including ourselves, saw it before, and that's not the part. The part that's the surprising part is the fact that you get good generalization even in noisy situation, even though you insist on zero training error in a noisy situation.
Yeah, but for instance, the paper by Mathieu Viard's group, and I think Julio is also Koto, where they observe the double descent in MNIST, I mean, that's intrinsically noisy because it's MNIST.
Okay, so I'm not. Well, we don't. Okay, I'm not familiar with the paper, I have to say, so I don't want to be the arbiter of credit here for sure. But at least from a statistical learning perspective, it wasn't clear. I mean, there are many papers that looked at zero interpolation solutions on MNIST. It's not completely clear, and this is maybe I think so maybe I'll show this. The real experiment that Misha did that I think convinced many people is this experiment, because for MNIST, when talking about MNIST, it's not completely clear that it's noisy. I don't know actually what the reality is in MNIST. Maybe the approximation error really is zero, right? And it's just that the error that we're seeing is all due to the estimation error, right? That we don't know that for sure. So what maybe I'll describe this experiment and so what Misha did was actually very explicitly took synthetic data and added noise, high levels of noise to synthetic data. Okay? So what we see here on the x-axis is the amount of noise added. Okay? And so the green line is the Bayes optimal predictor, right? So that just represents the noise that Misha added. Okay? And then you fit this using different methods that get a zero training error solution. So all these get zero training error solutions, and you ask what is the test error. Okay? And what you see is that the test error for all these methods, for all of them, okay, it's higher than Bayes error, of course, because you do have some estimation error. Okay? But for all of them, the test error is substantially below the null error, the null risk, which is here. So that means that even if you have, add 70% label noise, you then expect to get better than 70% error, of course, right? The question is what's the excess error you get. But our classic theory would tell us that if I chose a correct point on here, like some point here, then I would in fact get some 70% plus some excess error. I'd get good generalization, and this excess would shrink to zero as my number sample increases. But what we see is we get this even all the way down here, even if we insist on a zero error solution. Okay? And that's something that at least our classic statistical learning theory is not. That's not how we explain things. Okay, that's not how it's not set up to do that. So that does in fact require rethinking. So in particular, it seems that the phenomena we're seeing here is we are overfitting. We are definitely fitting the noise. Right? There's no doubt we're fitting the noise because I have 70% noise, and yet I'm getting zero training error. I must be fitting the noise. But the question is, how are we fitting the noise? And it seems that this fitting the noise, this overfitting, we're anyway talking about this overfitting, but this overfitting can be either harmful or benign. So if my complexity measures as degrees of polynomial, the overfitting is harmful in the sense that in order to fit the noise, I really have to change the function globally and completely mess up the solution. Whereas in some other situations, fitting the overfitting is benign. So what you get is this is just a cartoon. I completely drew this plot. It doesn't actually represent the result of any learning rule, but this is conceptually what happens, that you're still fitting the noise, but you're fitting the noise in a way that has kind of a measure zero effect. You're not, the fitting the noise doesn't actually ruin your fit in other places. And so it's not that it's useful for you to fit the noise necessarily. You're not maybe gaining by this, but it's benign. You're not losing. It doesn't, fitting the noise doesn't hurt you. Okay? And this is kind of some of what we're trying to understand, and I don't think I'll have time to get into this. Maybe one of the other instructors will, is understanding under what situations overfitting is harmful and under what situations overfitting is benign. So for example, for least square problems, we can get both types of behaviors. And I don't have the plot to flash. We can get both kind of behaviors in a predictable way. This is a result of research like in the past 2-3 years by Misha and Peter Bartlett and Ram in our group. We can know that it kind of relates to a measure of effective rank, the trace of the square of the covariance divided by the square of the trace of the covariance. If that's superlinear, we get benign overfitting. If it's sublinear, we get harmful overfitting. So we can kind of characterize these two situations. And I think characterizing more generally, this is very specific to well-specified least square problems, in understanding more generally, characterizing when, characterization of when we get harmful, when we get benign overfitting is, I think, one of the big challenges that we have now that, again, is fairly different from how we thought about overfitting previously. Sorry, I want to take
One small question about this, this nice cartoon about
Yes.
overfitting. How can one reconcile this with this idea that you were stating before about the fact that gradient descent or variance of it will favor some kind of smoothness criteria?
Okay, so the question is which what is the smoothness criteria? And in particular, the smoothness is in high dimensions. So one distinguishing characterization of benign overfitting, it requires very high dimensions. As I mentioned, for least square problems, for example, in order to get overfitting to be benign, I need the effective dimensionality to be superlinear in the number of observations. And so I think I don't have a I don't have a good intuitive answer. But in some sense, it's true that if I look at the smooth solution in low dimensions, overfitting would be harmful. I would not get benign overfitting. Okay, I don't exactly, understanding what smoothness means in high dimensions is very complicated. I don't, high dimensions is kind of inherently non-smooth. But I do, for least squares at least, I understand why. We can talk about later why in least squares, if you have very high dimension, then fitting the data, it's basically because, roughly it's because things are, everything is orthogonal, and so you can kind of fit the noise without affecting other things. I mean, it's a bit different than what you see in this cartoon, but the way the predictor will look like is exactly look like a good predictor, plus a component that fits the noise but is essentially zero. Okay. Yeah, I hope that roughly answers the question. Yes?
I'm not sure how much to take this recommendation that even the noisy regime we should interpolate. I mean, if we interpolate, so for example, you would have seen double descent if you have some regular, if you have some L2 density,
right.
You don't see double descent at all.
Yeah.
So I think in some sense we don't want to interpolate like hell.
Okay, so that's,
not too much.
okay. So that's completely true. Now I'm sorry, I don't have I have slides that exactly address this. So you're right. So the type, okay, maybe I'll try to just have here a plot that I don't have. So the right way to look at benign overfitting is, so what we said is that in these double descent curves, the x-axis is in some sense wrong, because whereas the x-axis is not complexity. Okay. So the right way to look at it, and I'm really sorry now I don't have this plot, is when you put the actual measure of complexity on the x-axis. Or rather than complexity, I'll put lambda. So think of minimizing the loss plus lambda times the regularizer, even just L2 regularizer in some high dimensional space. Okay, so you can think of it as or the RKHS norm. Okay, so the way, and now how this looks like. So harmful overfitting would look like this. Okay. Benign overfitting would look, so this is harmful overfitting. Benign overfitting, and we can actually show this even, I have plots, you can generate this in a predictable way again if you generate the data based on how the spectral decay, as you control the spectral decay, you can get either this behavior or this behavior for well-specified Gaussian problems. Okay, so benign overfitting would look like this. So again, what's going on here? Here, this is the MDL axis. Here, lambda. Actually, the way I wrote it here, think of this as lambda going to 0, and this is lambda infinity. Okay, so as lambda goes to 0, I have infinitesimal regularization. I'm basically looking at the minimum norm interpolating solution. Okay, so benign overfitting means that you don't really care too much about the regularization parameter. You have lots of flexibility. You have an entire, in terms of the curve that we have here. Where is it? Here, that there's an entire region here. This is maybe the optimal point, but anywhere along here it's fine. Okay, so there's an entire range of regularization parameters that's fine. So you don't care. It's exactly what you said, that you don't care too much if how much you regularize. If you under regularize, that's fine. Okay, or if you don't regularize at all, you just look at the minimum solution. And so indeed, I didn't actually say this as my recommendation, but it's true that, I'll answer your question in a second, that in some sense I think the most practical implication of this whole thinking of benign overfitting is that in many cases you don't have to worry about exactly too much about selecting lambda, selecting a regularization parameter. You have an entire regime here which you'll be fine. Not just over here, but this entire area, okay? But what you're saying is that actually in many cases what we see is something in between. It's something that goes down and then it doesn't explode, but it does go up a bit, okay? And I think this red curve is the typical situation we see. So on one hand, it doesn't fit our standard for harmful overfitting. Because even if I completely under-regularize, even if I look at the minimum norm interpolating solution, I still generalize well. But it's true that I can generalize even better by regularizing a bit. And this goes back actually to your question from before, in distinguishing between the big the important thing and the details. Okay? So if this is, this is maybe 5.6% error, and over here I have, I'm just making up these numbers, right? 5.4% error. Okay? And now it's true that by regularizing it definitely helps to regularize. I can reduce my error by 0.2%. It's not insignificant. Okay? But the big question is, how come I'm even getting here 5% error and not 90% error? Okay? And so this is still the part we don't understand. Okay? And in fact, what we're seeing is also we are this doesn't happen for well-specified Gaussian models. For well-specified linear Gaussian models, well-specified linear models, we only see either this or this. But we do understand now how in many cases, or we're starting to understand how in some cases you get in fact this red curve, which is like slightly harmful overfitting. And so and this matches exactly what we see empirically, that adding a bit of regularization is helpful, but still we can still understand how the system works even if with no regularization. Does that answer the question? Okay, excellent. So let me just wrap up. I see I'm not going to get to my second half of the talk today. Yeah.
Just one question about the figure of Turkey.
This figure? Yeah.
Yes. Why the kernels are performing better than the neural net?
Because in this specific data, I think, okay, so, something, I don't even know exactly when this is literally a figure copied from Misha's slides. I don't even remember what this neural net exactly is. I'm sure that if you wanted to you could come up with a neural net that would beat the kernel. Okay, why Misha? Part of Misha's I don't know if agenda, independent of this and this others, is to show that kernels actually can be as powerful as neural nets. So I think that's the kind of the sociological explanation for this. I wouldn't make too much out of it. Okay. Okay, so let's just summarize. I think I see I'm not going to get to the second half of my lecture, so we'll see what to do about that. Okay, but so just to summarize what we're seeing here, what fits our understanding and what doesn't. So we do understand, even based on our classic theory, and we can understand it even in linear models, which is really the only thing we really understand, how we can generalize even from situations we can fit random labels, right? So we have a non-uniform complexity control, and we can kind of be adaptive to the complexity, and we can understand how the complexity control comes purely from the optimization algorithm. And also in that case, how you can generalize better from bigger and bigger models, because they provide a better approximation of what we really want. And what we really need to ask then is just to kind of, in order to put this into our classical understanding, is ask, so okay, what is this complexity measure? If the complexity measure is not the size of the network, what is the complexity measure? And how is it minimized? And how does minimizing it actually ensure generalization? Okay. And then there's another issue here which really requires going back to, from my perspective, and again, maybe people understand it from other direction, but in terms of statistical learning theory, it does require going back to the fundamentals of statistical learning theory and understanding this phenomenon of benign overfitting. So that's maybe does require a bit more thinking. in what we're going to be looking at, the question we're trying to be answering in the next lecture. Actually, I started 5 minutes late, right? So I done. Okay, but I owe you a few minutes from last time. I think we'll wrap up soon. So. So as I said, the question we're trying we'll try to uncover is, what is, this true complexity measure, and the way we're going to try to address it is using this complexity measure approach. So what does a complexity measure approach mean? It means that we want to identify some complexity measure, and recall that my definition of complexity measure is any function from any mapping from my function class or my model class to the reals, or really it's just an ordering over functions. So we want to identify a complexity measure, and then argue that optimizing the algorithm actually biases us towards lower complexity. So, for example, keep in mind the complexity measure being Euclidean norm. So we understand how gradient descent prefers low Euclidean norm solution. Gradient descent will return the minimum Euclidean norm interpolating solution. So that's one part. We relate the optimization algorithm to complexity measure. Then we also have to understand why this complexity measure is actually good complexity measure. So we said in order to understand its good complexity measure, we have to understand how it can capture reality with small capacity. So to understand that, we have to both ask the statistical question of answering, calculating the capacity, of sublevel sets of this complexity measure. So this is a question about generalization, okay? And then also answer a question about reality, which is to say that reality actually has small complexity under this measure. And when we quantify small is again, so that the sublevel set that includes reality or approximates reality under this complexity measure is small, okay? And then I have to say that there's also a bit of subtlety here. It's not just enough to say that the optimization biases us towards low complexity. And this goes a bit maybe more towards Lenka's question before. We also have to say that the algorithm actually succeeds in optimizing it. So some of these complexity measures, or this complexity measure, even if we identify it, might be non-convex. For example, these, I think I erased it, but this 0.2 quasi-norm, we identified that as a complexity measure for deep neural networks. That's a non-convex complexity measure. It's a non-convex in fact, minimizing this 0.2 quasi-norm is a non-convex optimization problem. It's actually provably hard. It's an NP-hard problem. And so maybe one of you was too embarrassed to ask me, wait, I'm telling you that by training this network, deep convolutional network with gradient descent, I'm implicitly minimizing this 0.2 quasi-norm. How can I be saying that? It's actually computationally impossible to minimize the 0.2 quasi-norm in the worst case. So just by doing gradient descent on a network, I cannot possibly always minimize the 0.2 quasi-norm. Right? Really, what's the formal result that I can prove you is actually only that I'm going to converge to a second order stationary point of this quasi-norm. Okay? That doesn't necessarily mean I minimizes it because it's non-convex. And so this is, I think, still part of the question here to understand how everything here is non-convex. Not only to identify a complexity measure, but why is it that the algorithm actually, succeeds in minimizing it? Okay, and so I just want to emphasize here there are two different types of questions. There are mathematical questions. Mathematical questions that we can, by that I mean questions we can just study, on the board without ever looking at any data. Okay, so the two main mathematical questions is one is a question about algorithms. What's the bias of optimization algorithm, right? How, relating optimization algorithms into their implicit bias. And this is actually going to be what I'm going to be talking about in the next 3 lectures. So all my lectures are just going to be on this mathematical question. There's another mathematical question that I'm not going to be talking about, but hopefully maybe some other people are, which is understanding the statistical properties, right? So even after I identify the complexity measure, I'm not going to bother in my lectures in saying what is this implications in terms of generalization. So I'm going to say, oh, look, we see that this minimizes the L1 norm. That's great. I'm not going to ask the second question, which is how is minimizing the L1 norm actually good for generalization? Okay, but that's another question needs to be answered, okay, for all these complexity measures. And then there's a question, so these are two mathematical questions, right? Questions you can answer mathematically. But then there's another question which cannot be answered mathematically. In some sense, you can think of it as a scientific question because it's a question about reality. Okay? Suppose we identified some complexity measure. To say that this complexity measure is good, really, remember there are plots that we had at the beginning of the lecture last time. To say a complexity measure is good, just saying that you have sublevel sets of small capacity, that doesn't tell me anything. I mean, for any complexity measure, some sublevel set in hierarchy is going to have small capacity. right? Really what I need to say is how well does this complexity measure capture reality, right? Where does reality sit in the hierarchy of the sublevel sets for this complexity measure, okay? And that's ultimately a question about reality. I cannot answer this question without either reasoning about reality or actually measuring reality. Okay, so again, it says this is the question we're going to answer. So in particular, what we're going to be looking at is the relationship between optimization and learning. And so I think we're going to wrap up today, but the plan is as follows. So it's actually not going to be according to this order. We're not going to be talking about, I don't think we're going to be talking about benign overfitting. What we're going to do in the next lecture, I planned on doing it today, is we're going to actually, so I keep talking about the relationship between, I mentioned the word geometry several times, and this relationship between geometry and optimization and maybe learning. And so this is something that comes up also in the convex case, where in that case we understand actually pretty well the relationship between the optimization geometry and generalization properties and how they relate to each other. And I think that's a useful starting point, both because it allows us to develop this, intuitions about, geometry and optimization and local search, and because, it's a, I think we need to understand what we already understand before we start, going further. And also, it's going to provide us opportunity to talk about a specific optimization algorithm, which is going to be very important for us, which is mirror descent. So I'm curious, actually, how many people here are familiar with mirror descent? Okay, not so many. Okay, so this is what I'm going to do next lecture. And the end result of that, to some extent, is going to be defining and understanding mirror descent from several different perspectives. And then what we're going to do, starting from the second half of next lecture and into the last two lectures, is talk about characterizing the optimization, the implicit bias of different optimization algorithms. When I say different optimization algorithms, I really mean both different optimization algorithms and different parameterizations. And part of the things what we'll talk about is to see about how these are the same, because we're going to want to talk instead about talking about gradient descent in parameter space and then mapping. So we're going to look at things in kind of a dual way. Both we're going to try to understand what does gradient descent do in parameter space, just in parameter space, and then at the end map it to function space. But we're also going to take the other view, which is look at the dynamics in parameter space, look at the induced dynamic in function space. Now forget about parameter space and just think of it as local search in function space under some geometry. So we're going to take both of these views and see how, not surprising, we get the same answers, but some cases, one way is going to be more insightful or easier than the other. And that's what we're going to do in the mostly in the last two lectures, right? We have three more. So the next lectures are going to start being more and more analytic. I should warn you that my plan, at least, is this lecture is not going to be fully. It's going to be formal and unlike these lectures which are more just throwing ideas, but not going to be with full proofs. You can get. Maybe you can. People are less familiar with this. You can organize a tutorial. I can suggest to resources, and I think the notes will include it. When we get to the newer stuff, we're going to be more careful with actually deriving things carefully. Okay, I think that's it for today.
Thank you. So just a note to those who didn't pay their registration fees yet. Now is the moment to do it. Okay, go now.
Are they actually open?